So next speaker is Giongo from the University of Trento, Italy. His speech is about the assessment and retrofit of timber buildings. He's an associate professor at the Department of Civil, Environmental and Mechanical Engineering of the University of Trento in Italy. His research is related to the reduction of the seismic vulnerability of existing buildings and the design of timber structures. He was involved in several national and international projects, both research-based and industry-based. His research is characterized by an extensive experimental activity. He's member of the governing board of the Laboratory of Materials and Structures in Trento that I had pleasure to visit last year. And in that laboratory, the tests on full scales of structural elements play a very important role. And also on-site testing is one of the topics of his research activity. He's member of various standardization committees at national and international level, including the Eurocode 5 and the Eurocode 8 and the ASHE SEI 41 seismic assessment and retrofit of existing buildings. So I welcome Professor Giongo, and I yield the floor to him. Thank you.
Thank you, Luca, for the kind introduction, and good afternoon to everyone. Now you should be able to see my presentation, and I will also start by thanking Professor Rita Bento for the invitation. My presentation today, I will go over the main features of the new chapter 10, so a new chapter on specific rules for timber buildings, whose drafting was led by the subgroup on existing timber structure within the CEN/TC 250 SC8 Working Group 3, and that benefited from the preliminary activities carried out by the project team, and also by the from the interaction with the subgroup working on the masonry chapter. For the time being, chapter 10 focuses on three main structural components: timber diaphragms, timber frames, and carpentry connections that, of course, are also made of timber. My presentation will concern primarily timber diaphragms and the new user-friendly procedure to assess their in-plane performance and design effective retrofit, especially when the retrofit is also made of timber. In my presentation, I will try to present the new provisions as well as give some background information as much as possible. Aside from the time constraint, a good reason for talking in detail about diaphragms is that they play a major role in determining the seismic performance of existing masonry buildings, which constitute the majority of the building stock in those EU countries where the seismic hazard is the most relevant. Time and again, back when a major earthquake strikes, we see examples of walls collapsing out of plane because the too flexible diaphragms are incapable of offering an adequate restraint to the face-loaded walls, even in the case where the wall diaphragm connection is sound, such as this picture here, where you can see that the steel ties are still hanging from the roof. When the diaphragm are sufficiently strong and stiff, they can effectively transfer the inertial forces of the out-of-plane loaded walls to the walls responding in plane, and they can limit the impact of torsional phenomena, and also help transfer in-plane forces once the walls have reached their maximum in-plane capacity. But before delving into the diaphragm assessment procedure, it's worth reminding that carpentry connections are quite important too, as they affect the seismic behavior of existing timber roof diaphragms. All carpentry connections have been designed to transfer forces via direct contact, and they're quite good in doing so, so long as the force direction is that for which the joint has been designed for. When ground shaking occurs, seismic action may result in tension and shear forces that can dislodge the carpentry joint, unless some mechanical connection is provided. And here you can see an example from the 2012 Emilia earthquake, where the truss top cord is being pushed out of place, as you can see. And in Annex C, you find some indications on how to prevent that. And the key message is that you have to brace the carpentry connections with fasteners, such as bolts and screws, possibly without altering the joint static scheme that often is that of a hinge. Among the general rules within the chapter 10, we find guidance on how to obtain the design value for the mechanical properties of timber components. And as mentioned at the very beginning of today's webinar, there's this new, the introduction of this fifth factor, which is the condition assessment factor, that it's a parameter that depends on the condition rating and on the knowledge level that, according to the relation that we see here in the table. And as you can see, when the knowledge level is minimum, we take the fifth factor that corresponds to the worst degradation class among three. So we have three degradation classes, D1, D2, and D3. And if we reach an average knowledge level, then we take the phi value corresponding to the degradation class immediately worse than the one obtained on the basis of the inspection. And instead, if the knowledge level is high, then the factor is that of the condition rating resulting from the on-site inspection. Some specific instruction on how to reach a certain knowledge level when it comes to timber structures and timber assemblies can be found in the chapter 5. And of course, visual inspection is the base tool for determining the health condition of any timber component, and it should address each structural component. To reach higher level of knowledge, then visual inspection has to be supplemented by testing, relying mainly on non-destructive testing for knowledge level 2. While more invasive techniques such as semi-non-destructive techniques may be necessary to reach a higher level of knowledge. To help the designer select the optimal testing method according to the desired knowledge level, and also depending on the investigated parameter, table 10 is provided based on the recommendations drafted by the Royal Technical Committee, AST 215. And as you can see, there's a list of non-destructive and semi-destructive techniques. And for each one of them, we get an indication of what information we can obtain and how reliable such information may be. The application of, the applicability of a testing method depends on several factors, and therefore most methods are not mandatory, and their use must be determined case by case with a few exceptions. One of the parameters most important to the durability of timber structures and of wood in general is the moisture content. In fact, high values of the moisture content, when persistently above 20%, accelerate decay and also fungal attacks. And among the possible methods to estimate the moisture content, the electrical resistance method that you see a picture of here is probably the preferred technique to assess timber elements on site, as it combines rapidity of execution with sufficient accuracy, provided that the testing is done properly. And it's, of course, an indirect measure, as the method uses the positive correlation between the moisture content and the electrical conductance of wood. And of course, the measure is local and cannot go very deep into the material, but is very easy to perform, and it can therefore be easily repeated in several locations. For a higher knowledge, we need to be able to locate decay along and across the timber components, as well as try to quantify deterioration. So the resistance drilling method provides the relative density profile, such as the one that you see here, at a certain cross-section by measuring the resistance of wood to being drilled by a very small drill bit. And with such method, it is possible to locate decay and also inner voids, also in those areas, such as, for example, the beam ends or the joist ends that are often inaccessible and hidden from view, and that are the most critical because of the contact between wood and other hygroscopic materials, such as masonry, for example. Therefore, resistant drilling is mandatory if one wants to reach, if the goal is to reach a high knowledge level. There are, of course, other diagnostic techniques that allow for locating and quantify deterioration, and we don't have time to go into details, and that can be used to supplement the collected data depending on the situation. And one of the most common methods, although non-mandatory, as you can see from the asterisks in the table, is the needle penetration, which measures the wood resistance to penetration of a needle of given characteristics hit by a known impact force. And similar to the drilling method, this measurement is related to the material density. In this table here, we have the condition assessment factors for recommended for diaphragms, depending on the condition rating. And if the diaphragm is in good condition, we take 1 as the value of phi, down to 0.3 if the diaphragm is either classified as poor or we do not have enough knowledge about it. And respectively, if the diaphragm is being strengthened, then its performance is strongly influenced by the retrofit, and therefore we have higher values of phi. For timber, the conversion factor here can be replaced with the well-known K-mod factor that accounts for the load duration and the environmental condition, depending on the service classes and also the type of actions. And you can find the values in the PRN 1995-1-1 document. But let's go back to diaphragms. And when we look at timber diaphragms, we see structural assemblies that are composed of many components. And if we refer to the least complex configuration, such as the single straight sheathing that we have here, it comprises of floorboards, joists, nails, and sometimes blocking elements between the joists. Therefore, the overall in-plane response, it's contributed by the deformation of the timber components, of the connections, plus phenomena such as the board-to-board contact, interlocking, friction, which is especially important in the case of, for example, tongue and groove flooring. However, to keep things simple, it is quite common to consider timber diaphragms as ideal diaphragms made of a homogeneous fictitious material, and to adopt the so-called beam analogy, by which the diaphragm is treated like a beam, and so the diaphragm maximum deflection at midspan, delta here, includes flexural deformation and the shear deformation, which is expected to be prevalent given that this is a very squat beam. In the scientific literature dealing with diaphragms, there is the tendency to refer to an equivalent shear stiffness value, GD, which is obtained by considering the diaphragm as a beam subjected only to shear deformability. And with such assumption, our midspan deflection can therefore be estimated with a formula as simple as this one here, where this coefficient beta depends on the loading condition that are adopted. However, the GD value, so the equivalent shear stiffness value, is not just the shear modulus of the homogeneous material that I just mentioned, multiplied by the diaphragm thickness, but it's actually something different that takes into account also any flexural deformation. From the code point of view, and so from the chapter 10 point of view, the in-plane response of floor diaphragms depends on an effective value of the stiffness, and the effective stiffness of the floor depends on the reference value of the equivalent shear stiffness GD0, which is provided by this table here for as-built diaphragm and also for retrofitted diaphragms. And special attention is given to wood-based retrofits as they ensure good in-plate performance while limiting the addition of mass. But the question is now, where do these numbers come from? Well, the starting point was, of course, the experimental evidence. And here you can see some pictures from the testing, from cyclic testing done on full-scale diaphragms in the lab that was mentioned before by the chairman. And the results of various testing campaigns are available in the literature. And here I have reported a selection of pictures referring just to testing of unreinforced diaphragms, but many more examples are available. And in theory, by referring to an equivalent beam, one should be able to get free from the influence of geometry variations. However, when we compare different testing campaigns, it's not just the geometry that changes. There are also other parameters that influence the experimental results. For example, we have vintage diaphragms tested on site, and we have new specimens specifically built for the lab testing. We have tests done by loading the diaphragms parallel to the joist versus tests done perpendicular to the joist. Also, when we move from smaller specimen to bigger ones, some details are not scaled, such as, for example, the floorboard thickness, the nails, and so forth. So the results of all that is that for the same diaphragm typology, each research team recommends typically a value that is quite different from the other. And this is a problem. Therefore, it was necessary to find some shared interpretation keys, which allowed defining rules and provisions of general validity. And that was done via numerical simulations. And thanks to detailed modeling strategies where each resistance mechanism and deformation contributor was simulated by specific elements, it was possible to reproduce the experimental response of different testing scenarios without the need for specific calibration aside from geometry and material properties selection. And here you can see some examples of the good matching between the numerical and experimental curves. And after that, there was an extensive parametric study adopting different modeling approaches, analysis types, including nonlinear static analysis and nonlinear dynamic analysis. And the study allowed to isolate the influence of various phenomena, such as the aspect ratio or the scale factor. And also among the several aspects investigated with the parametric study was the panel layout for the retrofit solution with wood-based panel overlay. And as can be guessed from the bar charts here, the optimal choice appeared to be that of this herringbone pattern, and traces of such evidence can be found in the general recommendations for retrofitting the diaphragms that are reported in section 10.8, if I remember correctly. So in order to evaluate the expected deformation of the floor and carry out the safety checks according to the linear procedure that is introduced in chapter 10, one must first determine the demand with the very familiar formula here, where the total seismic force is acting on the diaphragm is proportional to the seismic mass, seismic weight, actually multiplied by the spectral acceleration. The diaphragm spectral acceleration, of course, accounts for possible dynamic amplification, depending on the relation that we have between the building natural period and the diaphragm period. So at this point, the natural question is, how do we calculate the diaphragm oscillating period? And consistently with the equivalent beam schematization that I mentioned earlier, we adopt the Rayleigh's quotient that you see reported here, where the coefficient alpha t here depends on the assumptions made on the load and mass distributions. And given the small differences, and also for the sake of simplicity, in chapter 10, a coefficient of 0.7 has been adopted similar to the choice made by the NZS-EE standard. So then the follow-up question is such theoretical value realistic? And to find out, there was some testing done in collaboration with University of Auckland, and testing was performed in New Zealand, in Wanganui, in a century-old building. And the photos here on the right show the testing setup. It is made of steel pulleys and wire ropes, and that was developed to carry out the snapback tests. Here you have the diaphragm periods obtained from the snapback tests at various deformation level, and also for different diaphragm configurations, including retrofit solutions such as renailing of the flooring or the application of a 9mm plywood overlay. And as you can see here from the last column of the table, the analytical values of the periods are in good agreement with the experimental evidence, with errors that are that do not exceed 90%. In addition to the condition assessment factor, the diaphragm shear effective stiffness is influenced also by the ratio AN over A that takes into account the presence of openings, and also by the alpha M factor that takes into account the stiffness of the face-loaded walls, and this is based on extensive research on the topic carried out and available in the literature. Even though it is not it is not accounted for in the formula for determining the equivalent shear stiffness, the role of perimeter chords is clarified in clause 10 8.2.2. And when diaphragms show a pronounced flexural response, as we can read over here, the chord axial stiffness is engaged, and the chords can actually act similarly to the flanges of a girder. And under such conditions, guidance on how to include the chord contributions into the diaphragm deformation can be found in internationally recognized documents such as ASE 41, which considers the flange effect and the chord splice contributions separately. However, and this is the really important part, single straight sheath diaphragms do not exhibit a clear flexural response, and the chord contribution is usually limited, as the steel chords, as you can see here, tend to show beam element type behavior instead of functioning as tie elements, as it is confirmed by both experimental and numerical evidence. Once we have determined the seismic load on the diaphragm, we can proceed to the safety check. And we can check if the diaphragm capacity is exceeded by deriving the unit shear force at the diaphragm support edges, and then comparing it to the diaphragm unit shear strength. The reference values for the unit shear strength are provided in table 10.4, depending on the type of retrofit and also on the loading direction. The diaphragm deformation has also to be checked, and it has to be done in terms of drift ratios, where delta D here, it's the diaphragm displacement demand at midspan, and LA is the distance between the diaphragm lateral supports. The displacement demand at the diaphragm midspan is obtained with this formula here, which relies on the beam equivalence that I've mentioned earlier. And the limits to the drift ratios are given in table 10.4 for the various diaphragm configurations and for different limit states. The Mu, the value, is the ductility factor that considers the influence of system nonlinearities on the displacement demand. And such value is related to the diaphragm behavior factor, as you see here, by adopting the equal energy principle. The recommended value for the diaphragm behavior factor is 1.5 for all diaphragm types, and it was selected based on extensive MER study. The provisions given in chapter 10 refer to single bay diaphragms. So work examples have been prepared to illustrate the application of the assessment procedure to multi-bay scenarios, as we typically have in real cases, such as this, where we have the timber floor and roof of a two-story residential masonry building. As you can see, due to the wall layout, just the joist orientation varies from bay to bay. And the interaction between the floor bays that are aligned in the direction parallel to the seismic force was, and is accounted for by referring to equivalent diaphragm that are obtained by averaging the shear stiffness of the interacting bays under the assumption of deformation compatibility, so equal deformation assumption. Walls that are oriented parallel to the seismic force is assumed as full restraints for the in-plane deformation of the floors, provided that such walls have sufficient strength and stiffness. So tentatively here, any wall that is at least 25% of the total width of the equivalent diaphragm is considered effective. And for this reason, for an earthquake acting along the X direction, the short wall here on the B wall line was not considered effective. And therefore, you see that the equivalent diaphragm SB spans from line A to line C. Here you can see the equivalent shear stiffness values calculated for the equivalent diaphragms, and the values range from the minimum of 150 to the maximum of 246 kilonewton per meter. The construction site selected for the case study is the municipality of Pelà in southern Italy, which is characterized by high seismic hazard. And once the else condition and the influence of the face-loaded walls are accounted for and factored in, then we get the effective stiffness values that you see reported here. And then we can determine the diaphragm periods and the force and displacement demands. The demand values determined with the assessment procedure outlined in chapter 10 were compared with the results obtained at the performance point of the pushover analysis performed on a finite element model, where the diaphragms were simulated using orthotropic shell elements that were calibrated on linear dynamic test data. And inevitably, there were some differences due to the simplifications on both sides, actually, even though the deformation difference was on average below 35%, with a tendency of the procedure to overestimate the model deformation. And in the simulation, in fact, all walls, no matter what their length, were modeled, and this resulted in smaller diaphragm deformations. A large underestimation of the deformation was instead observed for diaphragms SC and SD, and this was due to the failing of the wall on line 2 prior to reaching the performance point in the model. And so, having seen that, the strength of wall line 2 was also checked against the shear force transferred to it by the two diaphragms. So it's actually 50% of the inertial force related to the two diaphragms, and the calculated shear force exceeded the wall nominal capacity, and so it was in accordance with the model. And therefore, the diaphragm assessment procedure was performed again, but this time assuming an ineffective restraint at wall line 2. And that meant replacing diaphragms, equivalent diaphragm SC and SD with this one, this larger one, SF. And by doing that, the difference between the analytical and numerical expected deflection reduced significantly, with the hand-calculated value showing a small yet inevitable overestimation due to the fact that the model experienced a partial effectiveness of the aforementioned restraint, even after the maximum capacity of wall line 2 was exceeded. The tables in this slide show the safety checks according to the provisions, and for the diaphragms in the as-built and also retrofitted conditions. Thanks to because of the deformation compatibility assumption, the deformation checks are performed on the equivalent diaphragms. And what we see is that thanks to the relatively good deformation capacity of timber diaphragms, all diaphragms pass the check independently from the configuration. But it's worth reminding that such deformation limitation concerns exclusively the timber diaphragms, and that the compatibility with the deformation capacity of the masonry walls has to be checked separately according to provision in chapter 11. If we look at the force limitation checks on the right, we see that when the seismic force is acting on the y direction, the as-built straight sheath diaphragms do not meet the safety requirements and the pole must be strengthened. But when any of the timber-based retrofit described in section 10.8 is adopted, then it seems that it's sufficient to ensure that for this case study, the diaphragms meet the safety requirements. I've included some further references and background documents. And of course, there are some due acknowledgements. And given the time frame, I thank you for the attention. And welcome any question.
Thank you very much, Ivan, for the very clear presentation, also for the worked example, really helpful. There is a question. Are there any specific considerations for mass timber structures?
If they mean, if in the chapter I included specific provision for the assessment of mass timber structure, the answer unfortunately is, for the time being, no, there's no specific provisions for mass timber structures, but hopefully there will be in the next iteration.
Okay, thank you. I have also a very quick question. I see that this new clause encourage the use of timber stiffening intervention. That's very good because it's a light solution. I see reading the new version of the Eurocode 8 that for instance the old interventions with concrete based stiffening are still allowed, providing that you check the mass and the increase of the inertial forces. Could you please tell if it is, I mean, I understand this is possible or not. What do you think?
Yeah, no, I think that, yes, of course it's possible. The strengthening with the concrete slab on top of the existing diaphragms is also mentioned in the chapter, even though recommendations are for keeping the mass as small as possible and also try not to turn to invasive interventions, which are often accompanied to the concrete slab. So especially for the ring beams, when they're done by cutting the existing walls, that can alter the texture of the masonry. So, but that's, I think that are the some recommendations that also can be found in the masonry chapter. So as long as the timber diaphragm is concerned, yes, you can do that. And you can apply still the procedure that we have, that we can find in chapter 10. But of course, seismic areas, we all desire to keep the mass as small as possible.
Yeah, and the important experimental works that you did show that timber stiffening solutions are very efficient.
Yes, because there are also studies that show that sometimes rigid diaphragms are not even necessary and might be also detrimental. So you need enough stiffness and enough strength, not too much.
I agree. Thank you.
Thank you very much.
We are 15 minutes behind. I think we can, behind schedule, so we can move to the next speaker. Thank you very much, Professor Giongo, for your presentation.